So today's video is summarizing sections 6.5 and 6.6. What we did in the last section was talk about starting to make mixtures or solutions and see how the physical properties of a solution can be related to the physical properties of the components individually. For example, we had an equation that talked about the chemical potential. I see I have a typo right here. But it should make sense to you that the chemical potential of a component, let's say the solvent, in a solution is going to be equal to its chemical potential when that solvent is a pure sample, plus a term that's dependent on its concentration, in this case, concentration in the form of a mole fraction. Mole fractions are pretty easy to generate if you know the partial pressure of the solvent over its normal vapor pressure. Again, this is for an ideal solution where everything is behaving really nicely. Now, most solutions don't behave ideally, so you might expect that the math is going to be a little different. So that's what I say. We need to learn something new to express their chemical potentials. For non-ideal solutions, and what makes a solution non-ideal? Again, even though we're using the same vocabulary with gas laws, it's different. When a solution is non-ideal, it's because of unequal intermolecular forces. Remember, the new combinations of intermolecular forces are substantially different than the average of the two pure substances. In this section, we're going to use something that acts something like, I used the word something twice, an effective concentration called activity. What do I mean an effective concentration? Well, you might have a value of a concentration. Let's say some solvent, you have water, but when it's in a solution, the property is going to be related to how much of that solute is in the solvent, but not necessarily linearly proportional to how much you put in. It is linearly proportional to this thing that's called an activity. So the activity is the, quote, effective concentration. So what this is saying, if you have a non-ideal solution, the chemical potential of the solvent in this case is the chemical potential of the pure solvent plus a term that's dependent on the activity. Now, the activity is going to be what that solvent is acting like. It's an effective concentration. And so, similarly to what we had before, whatever the partial pressure is of the solvent over its pure pressure is what the activity is. It's usually something a little bit less than, although it could be more than, what the partial pressure would be if it was ideal. So we see that activities are related to concentrations by essentially a factor, something called the activity coefficient. It's a measure of deviation from ideal. So a solution that might be a 0.8 molar solution might act like a 0.7 molar solution. So that's what we mean by an effective concentration. And so you could make a substitution of the definition of activity into here, and you could see that two of the three terms are the same as they were up in 6.17. You do have this extra term here, the activity coefficient. Now, how do you go about getting these values in a lab? Basically, you need to find out what the partial pressure is over a range of concentrations. Now, you can't just have a meter to measure partial pressure. Usually what you do is you obtain the pressure of the whole solution. So obtain P first. So you figure out what the vapor pressure is of the whole solution, and then usually you need to condense that vapor to determine the mole fraction of the component in the vapor. Remember, this is a non-ideal solution, so you just can't assume that it's going to be related to the mole fraction. So you need to condense the vapor to determine the mole fraction that is present. Once you get that, then you can get the partial pressure due to your solvent. The equation that lets you do that is the mole fraction of that vapor times the total pressure will give you P1. Once you get P1, you can jump up to here and get the activity, and then the activity coefficient. So here's some data here that was generated in exactly that way. You could see that the experimenters made up 6 different solutions with urea as the solute. You measure they don't have the overall pressure here, but you measure the overall pressures, as we said, condense that vapor to get the mole fraction. And so then the mole fraction will allow you to write the mole fraction of your solvent. And then when that mole fraction is multiplied by the total pressure, you're going to get your vapor pressure due to the solvent. Then you can get your activity, and then finally the activity coefficient. So it's a little bit of work, but nothing too exotic. What about getting information about the solute? So you might remember the last time we met, we said there were cases when you can use Raoult's law and Henry's law for a non-ideal solution. Remember, that's when you're at the edges of those figures that we looked at, those pressure versus composition curves. If you're in that range where the mole fraction of one of the materials is like 0.9 or higher, or the solute is 0.1 or lower, those are called ideal dilute solutions. So you could just use Raoult's law and Henry's law. But what if you're somewhere else? What if you're not in that area? Well, you have to do something different. We're going to use activities. So the rest of this slide kind of derives how you're going to express the chemical potential of a solute. So essentially what you're seeing here is the chemical potential of the solute, I've labeled that with number 2, is going to be equal to a term that we're going to call the standard term, and a correction term, or a term that's based on the concentration of that solute. I do want to point out, though, and if you want to read the book carefully, you can learn some more or look on the web, that the standard state for the solute is actually a hypothetical standard state. It's a weird standard state. If you remember when we do Henry's law, I'm just going to kind of make something off the top here. Remember that it was just for a region very early when the mole fraction, let's say, is very, very small. The hypothetical standard state is this imaginary, pure version of the solute that has a partial pressure way up at the top equal to the Henry's law constant. So that's the standard state that we mean in there. And notice how they put a little circle there instead of the star. The star is the chemical potential of the pure material, but the standard state for equation 1624 includes this term, with this term allowing for the hypothetical standard state. For non-ideal solutions, so in areas that you can't use this equation, that's Henry's law area, you need to use an activity. Now the activity definition kind of follows what we had before. The activity is an effective mole fraction. The activity here is the activity coefficient times the mole fraction. And Henry's law then becomes this equation. Often, solutes are expressed not as mole fractions, but as molalities or molarities, especially if something is dilute. And what you see here is the molality version of chemical potential. Essentially, these figures on the bottom, I don't find they're too instructive, but they basically are showing you that a non-ideal solution is kind of pegged to this hypothetical ideal solution, again, represented by the black lines in each of those curves. That's essentially this standard state here. The correction term puts you at the right place on the red-brown line. All right. Now, something that's maybe a bit more practical. So what we have here is the derivation of some plots, and then we'll take a look at what we could do with the plots when we think about how they might be applied to a real situation. So here I have a nice clean derivation of expressing this pressure composition diagram. So if you define the partial pressure of benzene in a mixture as its mole fraction times the pure, and the partial pressure of the toluene as its mole fraction times the pure, you get a straight line. Remember, this is for an ideal mixture, where the average intermolecular force is about the same, where the new intermolecular forces, the intermolecular force between benzene and toluene is about the same as the average of the BB and the TT intermolecular forces. Okay? So I work this out, and what you see at the end of the derivation, if you choose the total pressure as the y-axis and you choose the mole fraction of the benzene as the x-axis, you get a straight line, and this is your slope. Okay? If you do a little bit of rearrangement, and you can see here, these are the equations I started off with. There's two different ways you could describe the partial pressure due to the benzene. You could either describe it as the mole fraction of the benzene times its pure vapor pressure, or it's the mole fraction of the vapor times the measured pressure. Those are the same. If I rearrange for the mole fraction in the vapor and substitute that into a rearranged version of the total pressure, you can get another linear arrangement. This curved line that you see right here in B is a plot of the total pressure of the mixture versus the mole fraction in the vapor of the benzene. Okay? Now, the combined plots are shown in C. Above the straight line, so this is at the high pressure version of the mixture, as you might expect, that's when you're going to have a liquid. If you lower the pressure enough, you're going to have a vapor. This is going to lead us to something that you've all done in organic chemistry, and I kind of mentioned it earlier. It's fractional dissolution. So, again, the stable phase at high pressure is the liquid, and at low pressure, the stable phase is the vapor. So what this diagram ends up giving us is a strategy for, separating the liquids. If I had a mixture, let's say, of 0.2 mole fraction benzene and 0.8 mole fraction toluene, that's starting me right here. So what this suggests is if I sort of put a vacuum on my flask and lower the pressure, you're going to start to see some vaporization. Basically, you're going to boil that liquid, and what this graph is telling you is that the content of the vapor is going to be at point B. The composition of the vapor is actually going to be 0.5 benzene and 0.5 toluene, just by pulling a vacuum on this mixture. If you condense that vapor, essentially go back to room pressure to take you to the liquid phase, and then do the same thing again, you're going to get a new vapor with composition D. And according by my naked eye, it looks like it's about 0.78 benzene and 0.22 toluene. Now, in practice, that's not how you separate mixtures, right? You set up a fractionating column, and you adjust the temperature. You don't adjust the pressure. So this is much more convenient. Although the diagram that I just showed you on this slide works perfectly well and would work if that's how you decided to separate the liquids, this is the one that we do in lab, and I'll show you that diagram on the next slide. One little thing here I want to mention again, those beads that are in the fractionating column are going to be in a minute. So this is a so-called temperature composition diagram. So notice how the stable phase is flipped from the previous diagram. If at the high temperature, the vapor is the more stable phase, and the liquid is the more stable phase at the cooler temperatures. But fractional distillation is based on taking a mixture. So this one here looks like maybe it's about 10% benzene, and if I'm down here at, let's say, room temperature, 25 degrees Celsius, the place I'm going to intersect with this line is the place that it's going to start boiling. And the content of the vapor is going to be over at B, which is a lot closer to 50-50. If I condense that vapor at point C and then boil that again, I'm actually going to get very, very rich in benzene vapor. So in your organic lab, you don't just do this once. You essentially do multiple of these, quote, theoretical plates by having the beads in your column. Each bead kind of acts as a condensation and vaporization site. As the beads heat up, then the material makes its way up the column. This is exactly how crude oil is separated into gasoline or kerosene or propane for your grill. You actually have hundreds of theoretical plates that separate the fractions of the crude oil by their boiling point. Now, the previous picture I showed you was for an ideal mixture. Most materials don't behave ideally. It's more complicated. This is a case of when you get azeotropes. So on the left-hand side here, remember when we had deviations? So a positive deviation from ideal is when you have weak intermolecular forces between A and B. And I gave you some examples here. So the left-hand side of the graph of a temperature composition graph is propanol water, ethanol water, carbon disulfide water. Now they're all going to have their own unique shapes, but what's going to be common to them is the presence of an azeotrope. Essentially in this case, it's going to be a mixture of the two materials that has the same composition in the liquid phase and the vapor phase. So it's sort of a minimum boiling point for the mixture. Alternatively, when you had mixtures that had negative deviations, those were ones when you had strong intermolecular forces between A and B. Our textbook author says that this is a much rarer situation, but they did give two examples. If you have chloroform and acetone and hydrochloric acid and water, you get a maximum boiling point spot. So some interesting things happen here. If I go to my original graph, let's say ethanol water, this one isn't labeled, but let's just pretend. I have about a 0.1 mole fraction of liquid 1. When it boils, so look what you're doing here, you're raising the temperature. Once, again, this isn't a bead column like I mentioned earlier, we're doing each of these as individual plates. But at the first sign of boiling, the vapor that you see is going to have this composition, maybe close to 0.3 in component 1. And then it could be cooled and boiled again to get composition D. The point is you could do this a couple of times, but you're eventually going to get to a material that has that sits right at that point. You're going to get a place that the condensed vapor has the same condensation as the liquid that boiled. So the same composition for the liquid and the vapor. Okay. Let's see here. What do I have? Oh, I don't want to neglect the point that the liquid remaining in the pot is getting richer in component 2. Okay, so you basically are constantly increasing the boiling point of that remaining liquid until eventually it would be pure. If you just kind of boiled off half of it and then cooled it down and boiled it off again, you're going to be constantly working your way to the left for the starting point of this graph. Again, just looking at the remaining liquid in the pot. On the right-hand side, the negative deviation example, if you look at starting point A, this looks like it's about 0.4 mole fraction of component 1. The vapor is going to be richer in component 2. Let's see, about a 0.22 mole fraction for the vapor in one and would be 0.78 in the other. If you condense that vapor and boiled it again, here the vapor is getting richer in component 2. Eventually, You can get pure component 2 by doing multiple theoretical plates for this type of mixture. The azeotrope, if you happen to start with a mixture that's precisely at the intersection on the bottom of the curve, the liquid would boil exactly at the tip-top temperature, and the composition of the vapor would be exactly the same as the liquid you started with. One thing I want to mention is that the composition of the azeotrope does depend on the applied pressure. Here's some data here for hydrochloric acid and water. I'm not sure why these percent weights are a little different, but I guess yes, of course. This means that the actual azeotrope point is going to slide a little bit to the right or left, depending on what the pressure is. I noticed that the boiling point has a more dramatic difference. So that's the temperature composition diagram for non-ideal solutions. One more example to look at, and that's on the next slide. Here we're going to look at solid-liquid temperature composition curves. So imagine starting with a liquid that's a mixture, and you cool it. Instead of doing on the previous slide, warming it till it boils, what if you cool it till it starts to form a solid? The freezing point of this solution is going to depend on the composition. The freezing point is always going to be lower than that of a pure solvent. So imagine here, seems maybe kind of an odd mixture, but they've got liquid, antimony, and lead. So it looks like you got to heat this up quite a bit. But point A looks like it's about, 40% lead and 60% antimony. If you cool that mixture, it's going to start freezing at point B. Again, as it said before, it's going to be less than the 631, the solvent, the majority one here. So this is what's interesting, though. At point B, the solid is pure B. So in this case, it's actually antimony. So what this is saying is, let's say I cooled this down to whatever this temperature is, cooled down my mixture. The solid that would appear would be pure antimony. The liquid that remains would have this composition. So liquid that remains. And then this is the solid. It's kind of cool. So as the temperature is lowered, more and more of the antimony is going to freeze, and the solution gets progressively richer in lead until the composition gets to this guy right here. Right before you hit E, you have what's called a eutectic, or this point is called the eutectic point. So at that point, if you had sort of separated, so you're just above point E, you've separated all the solid, which was pure antimony, and you still went colder, so you went down to whatever this temperature is down here. The solid would be a, quote, solid solution. The atoms of the lead and the antimony would be randomly dispersed in a solid. It would almost be like, it would be like an alloy, I guess you can think of it, in exactly that composition. You could start from the other side. You could start with mixture I. That looks like it's about 90% lead. And if you cooled it off till solids started forming, you would be forming pure lead as the solid first. And as you went cooler, you would get pure lead, pure lead, pure lead. Just before the whole thing freezes, then you would get a eutectic point for that solid solution. So that's something that may be a surprise to you, but that's what we see. We're actually told there's a practical eutectic mixture, solder, which is used in electronics boards, is 67% tin and 33% lead. And what that means is that that's a mixture that's right at the very bottom there, so that it freezes completely without separating between one component or the other. I did look at another textbook that had an interesting version of this. This was labeled as something as a reacting system. So notice that there are two different eutectic points for this composition, but they actually have the composition of a compound in the middle here. So this was claimed to be important in the, I mentioned electronics earlier, in the semiconductor industry, that gallium arsenide will actually form a compound in a one-to-one mixture. So what that's saying here is if I mixed liquid gallium and arsenide and started cooling it, the solid that would form would be a compound, gallium arsenide. The remaining liquid would get richer and richer and richer in, which one's to the right? I don't see. Let's just call it arsenic, until you got to a eutectic point down here. So I thought that was kind of interesting that you could actually sort of, I don't know if precipitate's the right word, but you could create a chemical compound solid by starting with the right mixture. On the other hand, this is kind of interesting maybe. If you started with a mixture that was only, let's say, 10% or 0.1 mole fraction in component B, forming the compound wouldn't happen at all, because you would hit this point, start forming a solid, and you would get pure A. Cool, 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 more. The liquid would get richer and richer in B until it reached a eutectic point. If you got rid of any of the solid just before that point, you'd pull off all the puree, and then you would get solid, this eutectic point at that point. So this is, I found to be just the beginning of some really interesting, cool temperature phase diagrams for mixtures. So I've got a few problems for you to work on before I see you tomorrow. I'd really like you to try to start on 19. 19 is a long problem. If you want to press ahead to try the whole thing, that's great. The first thing you have to do, though, is get out a graph. So get out your Excel and graph the pressure of, let's see, what's the data they give you here? Yeah, you want to do the partial pressures of each mixture versus the mole fraction of the carbon disulfide. You're going to get non-ideal curves from which I want you to get the Henry's Law constant. So I'm not exactly sure when I'll post answers for this, but give these a try, do your best, and I'll see you on Friday.